Good morning. Welcome back to EELE 461 561 Digital System Design. This is Brock. This video corresponds to our meeting time on Monday, April 6th. Okay, so we are continuing our coverage of crosstalk, and we're going to start moving into a different class of crosstalk, which is due to the return path. So if you recall, what we've looked at so far is when there is noise that is coupled onto a victim line due to a signal transition on an aggressor line. And that was kind of classic, right? You just look at the voltage on the wave that's traveling down the aggressor, and you look at the mutual capacitance, mutual inductance for a neighboring victim, and you look at how that wave puts noise onto it. Well, now we're going to look at a different class of crosstalk, which is due to the return path. Okay, so the impact of the return path of the aggressor on a victim. And this has a bunch of different nicknames. You probably have heard of some of these. Ground bounce is a really popular one. Power supply droop, simultaneous switching noise, SSN, and then simultaneous switching output noise, SSO. They all kind of describe the same phenomenon of you're looking at the coupling mechanism within the return path. Okay, so what is this whole idea of a return path anyway? So if you recall, this is, let's look at a printed circuit board transmission line. This is a microstrip where you have a signal trace above a ground plane. And we have always assumed that the ground is perfect. Okay, from day one in our study of electrical engineering, we always draw these circuits, and down here we draw this line, and it's assumed to be perfect, right? And we'll even put the little ground symbol on there, the little triangle. And what that means is that we assume that the return is an infinite sea of electrons, infinite sea of charge. And since it has so many electrons on it, it's so conductive that its impedance or its resistance is zero. And that's important because if something has an impedance or resistance of zero, it cannot develop a voltage. So V is equal to IR. If your R is zero, then you can never develop a voltage across it. And that's great because it's allowed us to study the impact of signal propagation, or not even signal propagation, but just how these things work, how our electric circuits works without worrying about this return or this ground. And so that's been awesome, right? And we derive all of our math on it and KVL, KCL, and life is good. Well, now what happens is that when you start transmitting, waves, you don't really have this notion of a ground anymore. It's not necessarily a zero voltage imperfect conductor. What it is it's a return path. So what we think about now is, notice that this circuit, it's still written as LCs, but it's actually a little bit more accurate because now I don't have that little triangle representing the ground. What I have is I look at the current as it returns, as it propagates down here. So I actually care about this return. So is there impedance in it? It's no longer, we actually, when you talk about signal integrity, people will look at you kind of weird if you call it ground because it's not the concept of a ground. It's always the concept of a return path. Okay, and so we'll stop calling it ground, even though I wrote ground right there. Okay, so why are we able to even pretend that it's kind of this ideal return path when we do a transmission line? Well, it's because this structure assumes that this ground plane or return plane is infinite. So it's huge compared to the signal. And when I say huge, I mean the width. If this is 6 mils, you're assuming that this is a couple inches, right? So that field lines don't ever see the edge of the return plane. Well, that's great as long as you're in a microstrip transmission line. What happens when you change geometries in order to go in and out of chips? So look at what happens here. So if you were on a ground or a return plane, it's hard to stop saying ground. So when I say ground, I mean return. When you come to a chip and you need to connect your signal and your ground, what do? Well, you just route your signal right into a package pin, but then the ground or return plane has to hit a via and come up. And so then what happens is that you via up and then you go through these little pins. And if I took a cross section of the pins, look at the geometry of the two signals now. So here's your signal and here's your return. They're both the same, and you can no longer say that this, the return path or ground is an infinite plane, right? It looks like a totally different structure. And it turns out that what happens is when you take this thing and condense it down into something like this, it looks highly inductive, okay? So what our model changes to is if you drew this as a circuit model, you have to now start putting in this little return path inductance. And it is dominated by inductance, so we rarely put the capacitance in here. What we do is we just model it as something that has become highly inductive. So this becomes the new inductive model. So now think about what happens there when you switch, right? They call it switching noise. You are going to move current through the return path, through this inductance. And that's why they start calling it switching noise. It's because you don't see the noise other than when you switch. Now, of course, that's how the signal crosstalk works too. But what happens with a chip is sometimes you have multiple signals that switch at the same time and use this as a return. So if you had, let's say you had one of those classic, dip packages, the ones we put in our breadboards, you might have 8 signals on here that all share a common ground pin. And all of them could switch at the same time in the same way, and you would pull 8 times the current through the return path, and you would see this huge inductive spike that causes the ground of the chip to be different than the ground of the printed circuit board. And that's why they call it ground bounce. And if you switch the other way, the return path then goes through the power supply pin, which again, on those dip packages, you only have one, then you call that power supply droop. And so those are where those terms come from. If you had 7 of them switch in the same way and only one was sitting still, you'd see this blip potentially on the ground. You'd see this blip on the ground. Well, if you were a signal and you were trying to hold at a 0 or a VCC, that ground or VCC changes the way you look like to the switching element. So there's chances you could actually accidentally flip a bit on one of the victims. And so this is why you see this thing called switching noise, simultaneous switching outputs, those terms. Okay, so let's see. Let's take a look at how you would model it. Well, it's pretty traditional. It's an inductor, L, D-I-D-T. But the L comes from the return pin inductance, which you usually you can get it through a field solver by pumping in the geometries, or you can just measure it. DIDT, we always want to switch back to voltage. So one of the things you can do is if you think about rise time and converting it back, we've done this before, but to get more accurate, if I wanted to convert rise time, or if I wanted to convert current into voltage, you could basically say V is equal to IR, I is equal to V over R. So you could take V over Z, and you say, well, how much are you swinging on V? Well, you care about how much you swing during the transition. So if you had a rise time, basically that's the 10 to 90. So more accurately, the amount of voltage that you swing is actually 80% of the amplitude of VA, or the aggressor, and then that corresponds to T rise. Okay, so if I had a 1 volt swing, the rise time is from 10 to 90, right? So that's an 80% of the voltage is changed during 1 T rise. So this is the more accurate representation of how you convert current over or DI to DT. And then of course you have the Z naught in there. Okay, well, how much noise do you see? You also have to multiply that by the number of signals that are switching. Okay, so then that's where you see this big factor. All right, so let's just take a look at what it would look like if you had one signal switch. So now I could go into ADS and I can build this model where I have, okay, I've got a Z naught and it comes down here and you have some circuit sitting over here, but the ground over, you want to look at like the difference between these two. Here's the trick when you go into ADS, you have to always have a ground, an ideal ground in a SPICE simulation. And so you're like, well, this kind of sucks because who am I measuring? So if you want to measure the ground bounce on the chip, which would be over here, so these are the inductors that model my pins, you'd put the ground over here, right? And then measure the bounce over here. But if you wanted to measure like the difference or the bounce relative to the printed circuit board, you put the ground over here. So it just depends on which one you're measuring. And what happens is that it'll change the polarity of this blip. So it just depends on where you're trying to look at the impact. So in this situation, let's say I had an inductance of 10 nanohenries and I was switching from 0 to 1. And you had an 800 picosecond rise time, which is pretty slow. You'd see like this 200 millivolt bump. And so whether it's a positive bump or a negative bump just depends on where you're looking with respect to the ideal ground in the SPICE simulation, okay? All right, and then there's also mutual inductance, okay? So if you think about the pins on there, you can actually have mutual inductance between the pins because they're pretty close together for the shape that they have. And so you can model mutual inductance. If you look at this, there's a little element in ADS called MUTIND, and you just drop it in there, and then you can give it the names of the two inductors that have coupling, and then you go in there and you put the it's a K, which is a coupling coefficient, and you give it the two names, and it'll actually show you how much voltage is coupled over here between these two. And so that's the little element that you can model how much mutual inductive coupling happens between the pins. Okay, that is it. And what we'll do is end there, and that kind of wraps up the coverage of crosstalk. We'll see ya.